It's a great pleasure to introduce Professor Vicki Stone, because she won't like me for reminding her of this, but 17 years ago this week, she took a chance on me as a PhD student. And Roger stole my joke earlier because I was going to say I look older than her now. So but there we are, I'll say it again. But thank you for coming, Vicki, and we look forward to your talk.
Thank you. I'll put this down here. Thank you very much for the invitation to Craig, Martin and Roger. I'm delighted to be here. I'm going to give you a bacon sandwich of a lecture. It's going to be a nice, crusty, freshly baked French loaf, but it's going to have vegan bacon in it. I'm sorry. So it's going to be a nice beginning and a nice end, and then the middle is going to be a bit rushed. So my title is A History of Nanotoxicology. So I'm starting with, let's call them the fathers rather than the grandfathers of nanotoxicology. So we have Anthony, who was one of the original authors with Ken Donaldson and Bill McNee, who wrote the first paper that suggested that the ultrafine particle fraction in air pollution was responsible for the toxicology of PM10 and other air pollutants. And that was based on some data out of Gunter Oberdorster's laboratory, which I'll show you in a minute. And that led to a COLT Foundation grant application on which I was funded, and it led to a plethora of other people becoming involved in particle toxicology, especially nanoparticles and air pollution. And this has expanded. So there are what used to be 5 groups in the world studying nano-sized particles or ultrafine particles, probably went up to hundreds of groups in the world studying that. So I hope you can see your faces on there. I couldn't get everybody. Not everybody has a web presence. Some people are quite dark on the web. Okay, so let's talk a little bit about nanomaterials and nanotechnology. So we all know that nanomaterials are in the nanoscale. There are various definitions for what a nanomaterial is. I won't go into those today, but we're looking at things, usually below 100 nanometers for at least 1 or 2 dimensions. So we're looking at things that are about the same size as proteins, DNA, lipids. So we're down at the molecular level. Coronavirus, for example, is a naturally occurring nanomaterial. But today I'm going to talk about engineered nanomaterials. And these come in a wide variety of shapes, compositions, surface chemistry. They have there's a full spectrum of physical and chemical characteristics that can be manipulated. The point is, they are not all the same. So when people talk about the toxicology of nanomaterials, you can't really say that. You have to talk about a specific type of nanomaterials or a specific subgroup of nanomaterials, because they differ widely in their physical and chemical properties, and they differ widely in their hazards. They're used in all kinds of applications. Nearly everything we use in our daily life could have nanomaterials incorporated into it or on its surface. Our clothing, our food packaging, children's toys, paints, cosmetics, sunscreens, electronics, you name it, it could include nanomaterials. So the potential for exposure to nanomaterials is relatively high because we're all using them on a regular basis, but it doesn't necessarily mean they're all going to have a risk associated with them because of this variation in toxicology. So as I've said, the first data on this was generated by Gunter Oberdorster's group in the 1990s when they looked at different sizes of titanium dioxide, and they found the smaller sizes of titanium dioxide were more likely to produce inflammation in the rat lung than the larger particles. And this led to a conversation between Anthony, Bill and Ken in the Canny Man pub in Edinburgh, and they came up with the ultrafine particle hypothesis, which explained that these smaller particles could promote inflammation and oxidative stress that would lead to cardiovascular responses. And when I moved to Edinburgh, we didn't focus on the cardiovascular responses. We were looking more at the promotion of inflammation and oxidative stress in the lung. So this was great. We generated some really nice papers. It was all very interesting. But then I would go to the European Respiratory Society meeting and Frank would say to me, so what's so special about these tiny particles? What makes them different from the large particles? And I would go, And we'd say it's something to do with surface area and the surface reactivity, but we didn't really have a good answer to that. And the reason we didn't have a good answer to that is because there were only toxicologists studying the problem. We didn't have a wide range of disciplines involved in the subject area. So then in 2004, the Royal Society and the Royal Academy of Engineering, Swiss Re, the insurance company, ESOTOC, an industrial collaborative group of people, scientists and forums, all these reports came out about nanotechnology and about how fantastic it was going to be. It was going to be really useful in lots of different applications, but for it to be useful in all these different applications, we need to be mindful of the safety of nanomaterials. And that led to a huge injection of cash, especially in the European Union. We had lots of grants from the European Commission to try and work out why nanomaterials are toxic, how they're toxic, are they all the same in their toxicity? And here's your vegan bacon in the middle of your sandwich. And this led to a lot of information that we can now use to understand the risks of nanomaterials. That ultrafine particle hypothesis has stood the test of time for most nanomaterials, not for everything. Usually smaller particles are more toxic, but not always. Surface area is definitely important. Reactive oxygen species and oxidative stress are definitely important for many nanomaterials. But we now have a much broader understanding of the range of physical and chemical characteristics, such as composition, charge, shape, that can influence toxicity. We're not just now focused on inhalation of these particles, we have data on ingestion hazards, dermal hazards, medical uses of nanomedicines. We have standardized protocols for assessing toxicity in vitro and in vivo. We have templates for generating that data. We have databases for bringing all of that data together. We have new ways of assessing exposure and for predicting exposure. So you can see there are lots of things that we have developed over the last few years, since 2014, nearly 20 years. I've put on the bottom two areas which I think we don't know, so are areas which I think there will be more information that we need to understand. We're very good at understanding the hazards at the point of entry into the body. So we understand hazards in the lung, the gut, and on the skin. But once it gets beyond that initial barrier and into the cardiovascular system and to the liver or to the brain, we're much less definite on that. Some really nice work from Edinburgh on the cardiovascular effects, but we need more on those other potential target sites. So we have a huge mountain to climb, or we did have a huge mountain to climb. There are over 26,000 chemicals or substances registered with the European Chemicals Agency under REACH, and out of those, about 300 of them are nanomaterials. But each one of those submissions isn't one nanomaterial. It's had lots of different forms. So, for example, you might have a dossier submitted on the silica nanoforms mentioned earlier, but within that dossier, there might be dozens of different forms of silica. So how can we assess the hazards and the risks of all of those different nanomaterials in a way that's not going to use too many animals? In the UK alone, in 2018, there were 3.5 million procedures on animals registered just in the UK, and a quarter of those were for regulatory purposes. So you can see, if we were to assess the hazard of all of those materials using animals worldwide, that would be ethically difficult to justify, would cost a lot of money, and it would take a lot of time to do it. And so the European Chemicals Agency allows you to group substances together for the purposes of considering risk, but they have to be similar to each other. And they use this word similar over 35 times within the regulation around this, but they never really describe what they mean by how you can assess similarity or how you can quantify similarity. But what they say is it needs to be similar in terms of physical and chemical characteristics, but also hazards to the environment or hazards to humans. And also you need to bring into that consideration some information about their fate and behavior in the environment and their toxicokinetics in the body. So it's not enough to say they're all high aspect ratio, they're therefore similar, and we're going to group them together. You need more information than that. And so the European Commission funded a project called Gracious, which was led by Harriet Watt. It started in 2018 and finished at the end of last year. And that project built a framework that allowed you to logically group together different nanoforms in a way that would allow you to take hazard information, animal data, from one nanoform and read it across or copy it across to a nanoform that lacked that data. And it provides a framework that allows you to justify that process. So this is a simple diagram of the framework. It starts off with either a single nanoform that you want to know more about and you want to see if there's a group out there that you can put your nanoform into, or a provisional group of nanoforms that you're interested in. And then it asks you to collect some basic information. So size, shape, and composition. Well, you should know those already. Maybe the surface area and if there are any impurities in there, but it's not a long, exhaustive list of characteristics at that point. We also need to know what you're going to use it for, because that allows us to work out where it's going to be released in the environment or where it's going to enter the human body. And we also want to know what's your purpose of assessing risk. Is it for ECHA? Is it for a regulatory purpose? Or are you at the early design stages of a new product and you want to build risk considerations and safety information into the design process? So once you've got that basic information, you can generate what's called a grouping hypothesis. And ECHA requires you to generate a hypothesis, which it explains the science behind why you would group different substances together. So this framework allows you to generate that hypothesis, and then it provides a systematic, tailored way to test that hypothesis so that you only gather the information that you need to test that hypothesis and you don't waste lots of time and money gathering data that you don't need. And once you've gone through that, you can either accept your grouping hypothesis and use it for read across, you can reject it and assess the risk on a case-by-case basis, or you can refine your grouping hypothesis and improve it. So I've said you can use it for regulatory dossiers, you can use it for safe by design, you can also use it to refine testing strategies in a research setting, and you can also use it in an occupational setting to inform precautionary measures. So if you have a substance that you're used to handling in a safe way in a factory environment, you could use the same procedures for another substance in the same group. So as I said, this framework allows you to generate a grouping hypothesis, but there are lots of different ways you can word a hypothesis. And actually, when people have tried to submit dossiers on grouping to ECHA, they always get knocked back because they're not sufficiently robust. So we came up with a template that allows people to generate a hypothesis that contains all of the information that's required. It considers the life cycle stage, so is it a pristine material, is it in a product, or is it something released at the end of life? And then these three questions: what they are, which are the phys-chem characteristics, where they go, so where they go in the environment or the body, and what they do, so those hazards. So those are three terms that you'll see cropping up in the REACH regulations now. And we generated 40 predefined hypotheses based on the literature information that was already available to us when we started the project. 17 for human hazard and 23 for environmental hazard. And then this template's available for people to make their own hypotheses if they want. So just a couple of examples of these hypotheses here. They build in the route of exposure. So this is the respiratory route of exposure. They build in some of the physical and chemical characteristics. Dissolution turn out to be really key phys-chem characteristics. Dissolution appears in all of the hypotheses. The dissolution rate determines how long your nanomaterial is retained as a nanomaterial in the body and how quickly it might release its molecular or ionic components, which may or may not be toxic. And so it allows you to identify whether you just need to assess the toxicity of the particle alone, the ions, or the combination of the two. The bottom hypothesis here is for the soil compartment for coated materials, and it talks about the stability of coatings on the outside of nanomaterials. And if that coating's not stable, then you can just compare it to the uncoated form of that same nanomaterial. So we have hypotheses for the respiratory system, the gut, the skin, the aquatic environment, sediments, soil, and for air. So how do you test that hypothesis? Well, the OECD came up with something called an IATA, an integrated approach for testing and assessment. This is a logical decision tree that helps you to structure toxicology testing. And what we've done is we've adapted that IATA approach and applied it to the grouping hypotheses. So we've developed IATAs for every single of those 40 grouping hypotheses. There is an IATA that allows you to logically test that. And the IATA includes these decision nodes or questions. This is a generic IATA here to show you that the IATA would include phys-chem characteristics that were specific to your hypothesis, information about which tissues or cell type are going to be exposed, and the mechanism of hazard. And if you say yes to all of the questions, you accept your grouping hypothesis. And if you say no at any point, you're kicked out of the IATA and you can reject or change your grouping hypothesis. So how do you answer each of those questions? There are multiple ways to answer each question. Everyone has their pet assays that they like to use for measuring specific things. So we generated some tiered testing strategies with simple in vitro methods or in silico methods as tier 1, more complex, three-dimensional, multicellular models of the lung, gut, or liver for tier 2, and then tier 3 in vivo models. And somebody was asking earlier on, how can we get these more complex in vitro models into the regulation? This is how you do it, by putting it into these IATAs and these tiered testing strategies. And what we found is that the tier 1 and tier 2 methods are more than sufficient for supporting industry in making safe by design options during the design process. And they're often all you need for a regulatory purpose, because usually within your group, one of your substances, one of your nanomaterials will already have in vivo data. So you only then need the in vitro data for all of them to compare them, to show that they're sufficiently similar to each other, and then you can just copy that in vivo data from that 1 or 2 members of the group to the rest of the group. So if you want to use this framework, it's been made into a blueprint, software blueprint, to allow it to be incorporated into risk assessment software. And that's been done by a couple of European projects. It's in the Sunshine project. It's in the Guide Nano tool now as well. And it's been tested online. It's been used by NIOSH. It's been used by the European Commission. It's been used by a number of consultants and industry who have tested it. It's gone through a whole panel of multi-walled carbon nanotubes from the NRCW, so it's been tested extensively, and it's now available as a document that will guide you step by step through how to use that. New projects such as Sunshine, Harmless, and Diagonal are extending that framework to allow it to be used for more advanced materials that are more complex in their structure. So it might be a nanomaterial with several substances within the same nanomaterial. So it's building in safety for those multi-component nanomaterials. But Sunshine is also bringing in sustainability as well into that consideration. And it's to bring in, from a sustainability point of view, the materials, the resources, the emissions, the energy use, etc., into that process. So that we're really progressing beyond assessing the toxicology of individual materials to safety and sustainability for groups of materials now. So in summary, there are too many substances to assess risk individually, takes too long, costs too much money, and importantly, uses too many animals. But you can use grouping to logically share data between similar substances, and this now has been applied via the Gracious framework to nanomaterials. And it can be used for not just regulatory purposes, but for informing safe by design processes. And this is now being extended to more complex multi-component nanomaterials, and it's incorporating sustainability considerations as well. So thank you very much for your attention.
Thanks very much, Vicki. Great talk as always. Time for 1 or 2 quick questions. Alison.
or is it also that the in vivo
It's usually for, I've not seen it done for a dose response yet, but there's lots of modeling. So at the moment, the similarity assessments, we've developed quantitative methods for that, but it's very much in a pairwise way. There are now multi-dimensional methods for similarity assessment being made, which will allow you to look at whole dose responses. So that's part of the new project. So hopefully we'll develop into that more dose response type assessment.
Matt?
How confident to eliminate part of the risk?
Yeah. Even with the current testing everything on a case-by-case basis, you still have that risk, okay? And one thing that I'm going to quote a guy called Robert Landsiedel now from BASF. Replacing animal with in vitro alternatives is not necessarily cheaper and quicker. It's because often you need a battery of tests. And so what you often find is with this, instead of having a single dose response in an animal, you now end up with a massive data matrix with about 20 lines of data for many substances, many controls side by side, in order to try and prevent that. Will it be 100% successful? Probably not, but then the current system isn't 100% successful either.
In the interest of time, I think we can leave the other questions to the networking event after.
Sorry, thank you.
No, you've not taken.
Oh, thank you.